other side of the planet here in Perth, in Western Australia. You'll see lots of pictures of Rio Tinto, big Rio Tinto iron ore trains in this presentation, because that's the heavy haul environment that I'm talking about. The presentation is about the work that we've done, essentially about the work that we've done, or so I should say some of the work that we've done with Rio Tinto, which is a long relationship. In my case, since 17 years now that I've been working with Rio Tinto as a customer since I joined. In fact, since I joined Hitachi when it was Unsaldo STS, so back in 2005. The intent here, this is a pretty simple presentation. I hope it doesn't become too simple, really it's just going to be some theory that I'm going to talk to you about, and then some case studies that we did, some work that we did do with Rio Tinto that demonstrates where we did apply some of this theory that I'm talking about, and then I'll draw a few probably rather obvious conclusions. So just to keep us all on the same page and to make sure that we really are talking the same language, I thought I'd just throw up a few definitions of systems assurance and a definition of systems integration here. Probably you can find 100 definitions of these terms on the internet, but these were a few that caught my interest from NIST, which is an American organization, standards organization, RISB, which is the Australian Rail Safety Organization, and Gartner, which is again an American consultancy. And essentially the NIST definition is about the system doing what its requirements say that it's going to do, whereas RISB's definition is focused on system safety assurance and the system doing what its safety requirements say that it should do, so far, so that the system is safe so far as is reasonably practicable. That's a framework, safety framework that we have here in Australia, which is in many ways similar to ALARP, which is probably familiar to lots of safety people from UK, but in some ways different, and comes out of the Rail Safety National Law that applies in the Australian context. And then systems integration. Well, I was interested by what Ian Gibson mentioned about emergent systems, because that's probably on the most extreme end of what we mean by systems integration, taking a collection of subsystems, components, or systems and combining them together so that the end thing realizes some set of requirements that we've defined. And yeah, the emergent systems that Ian was looking at, you may not even have defined requirements. So that's that's possible. So this presentation isn't about all of the stuff that Hitachi does. That would be impossible. I wanted to focus on requirements, and the thing about requirements is that requirements are hard to derive or define, because we need to derive requirements properly. We need to coordinate a lot of different stakeholders. And here I'm listing just a few of them: operator, integrator, suppliers, developers, and there's more than this. Obviously, I didn't mention users. That's an obvious one. And this need to coordinate all of these stakeholders leads to waste, inefficiencies, and waste. So what we want to overcome, or what we've been very interested in overcoming in our work with Rio Tinto, is this process waste. And the thing that we're most interested in is the flow of these requirements through the system life cycle. So that the flow from the requirement, the beginning requirement, through the process until we have an end product that delivers the function specified by that requirement. And that focus on flow is something that's also important to lean process methodologies, which are lean process methodologies are based essentially upon deriving methods and tools which fulfills some overarching values and principles. So the idea with lean, one of the ideas, sorry, with lean is that you should first start with the high level values and principles that you're trying to reach. In this case, the values that we're talking about are things like, these are values coming out of Hitachi's organization itself, but it matches with what we're trying to do with Rio Tinto. For example, sincerity, working in a transparent and honest way with the customer, which has led to principles like this one about early life cycle communication of information, transparent early life cycle communication of information between us as the supplier and Rio Tinto, who in many ways as customer are also the integrator of this overall system, which could be viewed, I think can be viewed as also a system of systems, because we're not the only supplier to Rio Tinto and not the only system that is being integrated. And so Hitachi has developed methods and tools documented in our GBMS that help us to perform the work in this collaborative and transparent way. So that's the most complex slide, I think, in this presentation. So this is the life cycle that I'm talking about. Probably this is the life cycle from the EN 50126. That's the railway standard from the Senelec, the standard that we follow, obviously, for our work. I think these sorts of V life cycles are very familiar to most systems engineers, and they appear in lots of standards. They appear in the 15288, which is the generic systems engineering standard, which I'm sure most people know, but also in the automotive and other fields such as marine and aviation, where if you look at these standards like 26262 and etc., you'll find very similar concepts as this. So I think without really being able to empirically demonstrate that, because obviously I haven't gone and worked in the marine field, for example, I think the things that I'm talking about here are probably transferable into these other domains. That's highly likely, and probably you find people that are talking about similar things in these other domains. And there's the V life cycle has this idea about developing and verifying something, and then integrating and validating that thing. That's the typical flow, the workflow. So when we think about these systems from an intermodal perspective, there are some challenges. Some of the things that we've observed in our work with Rio Tinto is that analysis of risks, whatever they are, whether they're safety or availability, are typically from a single transport mode perspective. And for example, can be from the perspective of the railway, or can be from the perspective of the road users. In the case of Rio Tinto, the two particular transport modes that they have interacting are rail and road. And rail and road, that can be a road that's public or road that's private. And the way that that's managed typically, these intermodal interfaces, is by transfer of hazards and application conditions between the different systems. But this is not obviously not a particularly efficient way to manage these transfer of risks. So the implication is that an overarching system of systems approach is more effective in ensuring that there isn't some risk that slips between the cracks and isn't managed, leading to a safety or availability issue for that system. And the conclusion we reached from our work was that there is the need for this overall integrator role, system of systems integrator, I mean, since the integrator is nothing new, of course, which can also be exercised by an organization such as the railway operator. And in fact, in the case of Rio Tinto, that's exactly what has happened. So Rio Tinto, as the operator, is also active as the integrator. And so when we derive these requirements, we are also needing to take account of all of the factors in respect of where there can be risk being generated, not just within the systems themselves, but also within the way that the systems are being operated and maintained. So all of these factors, and this is a diagram from the Senelec, by the way, which probably any railway people here will have recognized. I didn't draw this. And so all of these factors can lead to either safety or availability issues for that, that overall system. So when we derive requirements, we're also deriving performance targets or criteria for the system, or documenting performance targets or criteria for that system, or for the components or subsystems or composing systems of that system. And so when we do that work, we need to take into account the risk tolerability criteria that we're going to assign, or we do take into account the risk tolerability criteria. So risk tolerability criteria, that's something that is again documented in most of these system standards. In the Senelec, at least, there has now been accepted the common safety method approach, which talks about managing risk by reference to reference systems and codes of practice, as well as making explicit risk estimations. And coming out of that, we have things like safety integrity levels and availability and reliability requirements, and which in the Australian context have to always be considered in the context of the so far as is reasonably practicable regime. And what this SFARP means for people here in the conference who aren't in the Australian domain is that, or the difference from a LARP is that there isn't a fixed measure of what can be a safe level of risk or safe level of residual risk. If I just pop over to this slide here, that when we talk about what is the tolerable risk, SFARP, when you talk about SFARP, this tolerable risk here isn't necessarily in a fixed place, but depends a little bit upon what options are available to you to reduce risk. So if there's an option to reduce risk further, as shown in this particular diagram here, below wherever you currently have it, then so if you say you have reduced risk to this point here, but you could reduce it further without very much additional cost, then the obligation in SFARP is that, or what SFARP says is that you should do that thing that is reasonable, because the cost is not beyond or compared to the risk of loss of life or injury is not unreasonable. Can I go back to the other slide? Yeah, so I was just drawing this little fault tree here, which doesn't really show anything much, unfortunately, because I didn't want to put up in here in these slides anything that was really proprietary Rio Tinto knowledge. But what I drew the fault tree because, in fact, we did use fault trees to document this this assignment of performance criteria to the requirements that are applicable for the various parts of the system. Yeah, so this, I think, this is again based on a diagram from the Senelec as well, just talking about reduction of risk obviously has to be below the measure of tolerability. Okay, so that was just a really quite quick run through of the theory, and then I'll make a rather quick run through now of just a few minutes of the case studies. So where did we apply this? Well, we had a system for obstruction detection at level crossings, which was laser based, and that system is very interesting because obviously the thing that's most interesting about that is that the laser technology is not foolproof. There's plenty of ways that you can get under or around the laser technology with not being detected. And that's the interesting thing. So from a safety acceptability perspective, it was actually quite complex for us to determine if or when this system was safe enough. And because we had to configure this system in a way so that it was both detecting people and keeping the crossing safe if someone goes onto the crossing when they shouldn't do. So if the boom gates are down, they shouldn't go on the crossing, the system should detect them. But it also, you don't want the system to be making false alarms and stopping trains unnecessarily. So you've got this balance that you have to achieve. That was really quite tricky. So this diagram here was just a diagram that I threw in talking about a particular improvement we made to the system, coming back to that SAFARP topic, to add a SIL4 communications channel. So this ODS system is not SIL4 overall, but we decided it was SAFARP to add the SIL4 communications channel because the cost of doing that was really quite low, and there was a definite benefit for safety, even if the overall end-to-end result of the system was still not SIL4. Then we have another system that we developed, which is the banker system. These two locomotives here, this train is going in this direction, and these two locomotives are pushing the train. So at the back of the train, so it's not what you think. This is the back of the train. The locomotives are pushing the train in this direction, and these are called banker locomotives because they help the train up a bank. And so this system was complex because we needed to devise a technology that would allow us to separate these locomotives from the train while the train was running, and then automatically stop the locomotives. So I think I forget to mention here that the Rio Tinto system, the order hall system, is a fully automated driverless system. So the locomotives at the front of this train have no driver on them. And the locomotives on these bankers have a driver, but the driver's only there in a supervisory capacity. The only action the driver takes is to confirm that the bankers did separate from the train. And from that point on, all of the actions of the bankers are autonomous. Obviously, that can go terribly wrong if the banker locomotives decide to apply the brakes while they're still attached to the train, or if they decide not to stop after they detach from the train. And so the hazard analysis associated with this was terribly complex. To put other things into the mix, you've got work crews that work alongside the track, which will come to in the next example, and that also could be run over by these banker locomotives, which are misbehaving. That's a rather useless slide where I had to blur it out, which was showing the scenarios that we used in order to make this hazard analysis for the banker system. Scenarios showing what the system was doing and what the people were doing in each case. And then the last example here is the handheld possession terminal. This is a product that Hitachi is working on, or that we have, rather, I should say now, or had been working on, which allows a safer way for work crews to take possession of an area of track. Taking possession of an area of track means that the work crew can exclude, in particular, trains from entering that area of track, and thus it is a way of keeping the work crew safe. That's the primary function for this particular handheld possession terminal. Obviously, you could dream up many functions for such a device. One of the limitations you have is what level of safety integrity that such a device can achieve. And then, so based on that, the use of the device needs to be appropriately managed. What I mean by that is that the procedures that are applied for the use of the device need to be appropriate in connection with the level of safety that the device itself is able to achieve. What if the device provides a wrong information? Then would the people who are using it still be safe enough? And do they have other mechanisms by which they can cross-check, for example, the information they're receiving from the device? So this is this handheld possession terminal works hand in glove with the automated train system, because the automated trains, obviously, in the past, when you had drivers, at least you had a driver who could notice when somebody was in the wrong place. But obviously, the automated train isn't really going to be able to do that. That said, there are systems under investigation for the train to be able to look ahead down the track and see things that are on the track and identify what they are, and it generates appropriate alarms for people to make decisions on. So now, how do I go for time here?
Hi, Andrew. Yeah, I was about to jump in. It's probably time to wrap up for a couple of Q&A.
Yeah, we're there. So we just got some conclusions here, which is and do I have time to read those, or Martin?
Quick whistle through. Quick whistle through.
Yeah. Look, it's not. It's almost useless for me to read them, but anyway. So the 4 key focuses that you've got a system of systems integrator. They're involved early in the life cycle. The supplier engages with them, and the 2 parties bring together their relevant expertise. So you identify mismatches early, and you ensure collaboration. There you go. It's done. So that was fast, wasn't it? So now
thank you very much for that, Andrew. So first of all, I guess one question that just sprung straight to mind, there was one I put further up in the chat that Stephen's replied to that would be interesting to get your view on that by text later, if that's okay. But one that was more prominent that came to mind with the handheld terminals that you talked about for possessions was, I guess, the trick around that I see with systems engineering and systems integration is, how do you develop new technology into legacy systems? What if the legacy system as such causes your new solution to just not comply to current standards?
Well, yeah, well, that's one of the ongoing challenges. So I guess that in a way, that's why the IESM and the resulting changes to the CENELEC for the 5126 that were introduced in 2017, that's a driving force behind some of those changes, because really what the changes said was that to some extent you've got a right to rely upon reference arguments or code of practice arguments. So if you've got a legacy system and it's been working for a long time, then you might be able to argue that thing is a reference system, and whatever it's doing, the way that it's doing it is can be regarded then as safe, or in conjunction with some set of procedures that people are using. So what that allows you to do then is say, okay, but we're not going to really reanalyze the requirements for this thing. We're going to re-implement this thing perhaps on a new platform or new technology, but without opening the can of worms about why or whether this is safe enough, because it's been proven. It's a bit of a variant on the old grandfather rights thing, which has been around since donkey's years.
Brilliant. And then just one other sort of quick fire question as such, for how quick we can make it. So an interesting example, this is from Stephen, an interesting example of multi-mode that he's witnessed is an autonomous track inspection robot that travels on rails for inspection, but has rotors so it can move between rails. And I've seen them with road track vehicles as well. How do you create a safety case for vehicles that actually do go on multiple infrastructure sets?
Yeah, this is the challenge. This is one of the things that so we don't have, Rio Tinto don't have those sorts of vehicles in this moment. But if they did, that would present a systems challenge for us to integrate those 2 systems and keep them those 2 robots separated. But we do have other vehicles like high rails, for example, that are out there on the track, and Rio Tinto have other separate systems. Some of them developed in conjunction with Hitachi, and some not, that are keeping those high rails safe and separated from the automated trains. And so I think, and that's where I think the role of Rio Tinto as operator has blurred or become a role as an integrator, because if they didn't do that, probably the resulting emergent outcome would be probably not very safe, I imagine. So I think it's another example. I didn't mention it specifically, but yeah, that's another example of where this sort of stuff is working in practice. And just before you go, these YouTube videos here, I highly recommend to have a look at them, especially the second one. Very impressive. They're all stuff that Rio Tinto has published themselves because they're proud as punch of the system. Yeah, so go and have a look.
Great stuff. Thank you very much, Andrew.